All right, number 8, the graph of f prime is given here. This is the derivative of f, not the graph of f itself. The question says, where, if any, does the function have a local maximum and or minimum? An inflection point, where is the function increasing or decreasing? Where is the function concave up and down? Why? Explain your reasoning. Okay, first of all, this is very deceptive, maybe misleading, because we are so used to looking at the graph of f. Okay, you may look at this and say, well, clearly the graph has no maximum or minimum, local or otherwise. And that's true if you look at f prime, but f of x may actually have a maximum or minimum. All right, so let's think really carefully at this. All right, this is a hard question, but it pays to pay close attention to this, because I think this is really a kind of question that would demonstrate your understanding of the function, its derivative, and its second derivative. All right, let's look at this point origin. Okay, what's happening here? Well, all right, so one thing you should know is f is increasing, and that would be equivalent to the derivative of f positive, right? So the question is, where is this derivative function positive? Okay, and I think you can easily say positive means that it's above the x-axis, right? So it's this whole part here, right? So this is where this is true. F prime is positive on, it seems like f 0 to infinity. Whenever x is positive, okay, so I'm talking about this side here, right? You can see f prime is positive, and that's when it's increasing. Function is increasing. F is decreasing precisely when f prime is negative, or this graph, which is f prime, is negative below the x-axis. That's this part here, right? So that is on negative infinity to 0, only the left-hand side. Okay, so that's it. And then where is f concave up? Concave up means that the second derivative is positive, right? And that means the derivative itself is increasing. All right, do you see where it's increasing? F prime is increasing where? Well, if as you go from left to right, you know, as x increases, f prime is increasing. 0, the derivative is 0 at one single point, and then increasing. Okay, so this is actually on the entire line from negative to positive infinity. If the original function f must be concave up everywhere, because the derivative is always increasing, right? And so that's a tricky part. Now, what does the graph look like then? Oh, by the way, yeah, we can answer other questions here. If f is increasing on the positive side and decreasing on the negative side, okay, together, they will tell you that f has a local what? Maximum? No, local minimum at x is equal to 0. How do I know this? Well, because the derivative goes, look at the graph of this f prime. The derivative goes from negative to positive, right? The derivative changes from negative to positive at 0. And so when that happens by the first derivative test, the function f has to have a local minimum, okay? It does not have a local maximum because there's no point where the derivative goes from positive to negative, okay? And not only that, because the second derivative is 0, is greater than 0 at every point, or the first derivative is always increasing, this tells you that there is no, f has no inflection point. Because if you do have an inflection point, the second derivative should be 0 at some point, which means the first derivative is what? Well, you know, if the second derivative is positive, that means f prime is increasing. It seems to be increasing at every point. There's no point where the so what happens? Let me just explain this more carefully here. F has an inflection point, let's say at c, okay? That would mean that the derivative of the second derivative is 0, all right? And that means that the first, what do we know about the first derivative? Okay, well, we don't know, but the first derivative must have a horizontal, well, I should say, f has an inflection point at x is equal to c. That means f prime is 0 at that point, and changes its sign. In other words, f double prime must go from negative to positive, which means concave down to concave up, or positive to negative, which means concave up to concave down, right? In this graph, however, of f prime, there's no place where f prime is changing, or f double prime is changing its sign. F double prime, which is the derivative of f prime, seems to be, because f prime is increasing at every point, it doesn't seem like f double prime has change of signs at all, okay? So basically what this is saying is, let's just try to guess what the function itself should look like, right? We know that f is increasing on the positive side and decreasing on the negative side, okay? And so we're talking about a graph that looks something like this. Yeah, maybe. I don't know. See, the thing is, we don't know what this point is. We can't precisely draw the graph of f because we are missing a lot of information. Based solely on the derivative function, the graph of the derivative function, we cannot retrieve the original function. But we do know, okay, we do know that f is increasing to the right of the y-axis and decreasing to the left of the y-axis. All right, and there is no inflection point. Okay, and notice here, by the way, this function looks very much like x cubed. It doesn't say that, but it looks like x cubed, right? So what kind of a function do you know whose derivative? That's f prime, right? What kind of a function do you know whose derivative is x cubed? Now, this goes to like the question of section 4.10, but if you try to find the function whose derivative is x cubed, that's called an antiderivative of x cubed. That would be 1/4 x to the fourth, right? Plus some constant, okay? Anything like this is going to have this as the derivative. So the graph is actually going to be probably a 4th degree polynomial function, which will look like this, okay? And so that, now we don't know this yet. We don't know if this really is the function f, but we do know the graph should look like this because of all the information given about f prime. Okay, like I said, it is a tricky question, but it is worth spending your time trying to understand that. Okay, number 9, prove that any rectangle whose perimeter is 60 inches cannot have an area bigger than 225 square centimeters. So you do have to, okay, so this is a sort of an optimization problem, right? You have the square, let's call this x and y, and we are given that so the perimeter is 60 inches. What's the parameter? Well, you have 2 x sides and 2 y sides, right? So it's 2x plus 2y. That's the parameter of this rectangle, and that's 60 inches. And that means x plus y is 30, y is negative x plus 30, or 30 minus x. Okay, now this is called the constraint of this optimization problem. Now we are to optimize, in this case, I think we are trying to optimize what? The area. Area is xy. Well, you don't want to have 2 variables, so try to write the area A in terms of x only, and that is x times, instead of y, we can use this expression, right? So that's negative x squared plus 30x. Take the derivative. By the way, we know x is going to be greater than or equal to 0. It can't even be equal to 0, because if x were 0, then y would be 30. But there would be no rectangle. It'll be just a flattened rectangle, which is not a rectangle at all. By the way, x can't be bigger than 30 either. just because if x is 30, y would be 0, and again, the area would be 0. Okay, so we do actually have a bound or an interval on which this function is defined. The derivative is negative 2x plus 30, right? And you can set this equal to 0 to find the critical point. X is going to be 15. In this case, y is 30 minus x, so that's also 15, right? Now, if you look at the function here, you know, when x is equal to 0, xy is, of course, it's going to be 0. And when x is 30, x times y will be 30 times 0, because if x is 30, then y is 0. And so then xy would be 0, right? So the graph is going to be an upside down parabola like this. Okay, we found the one and only one critical point, which happens to be at 15. And right at that point, okay, what's the second derivative? It's negative 2. And so 15, so A has a local maximum because the second derivative is negative. That's a second derivative test at x is equal to 15. Okay, and from this picture, you can see it's also an absolute maximum because the endpoints will both give the area of 0. So the maximum area is going to be 15 times 15, which is 225 squared inches as desired. Okay, so no matter what you do, as long as x and y satisfy this constraint that the parameter is 60 inches, you cannot create a rectangle whose area is bigger than 225. And in fact, at that point, that rectangle happens to be a square, 15 by 15 square. All right, number 10, find the positive real numbers x and y. Okay, so you're given that these are positive numbers such that the sum is 6. And x plus 1/2 y squared is minimum. All right, so that's the function that we want to define, right? So minimize f, which is that. Okay, well, this time it seems like you want to solve this for x. X is what? 6 minus y. Let's write this as y minus 6. Okay, x is, no, that's not true. X is negative y plus 6. Okay, or x is 6 minus y, right? So x is negative y plus 6. And the reason is because this expression is easier if you substitute x as negative y plus 6 as opposed to the other way around. All right, so f of y, let's write f of y, which is x plus 1/2 y squared, but I don't want to use x here. So instead of x, I'm going to use this expression. So that is actually, what is that? X plus 1/2 y, right? Where this expression represents x. So we will try to minimize this. Trying to minimize this. How do you do that? Well, you take the derivative and set that equal to 0. It's negative 1 plus, now if you plug in, or if you do the power rule on that, it's 2 over 2 times y to the first power. So that's basically it. You set this equal to 0, you see that y must be equal to 1. Okay, the second derivative is simply 1, right? And so the graph, what does the graph look like? X and y have to be positive. If x is 0, y is 6, right? If x is 0, oh, no. Let's say this is a function of y. If y is 0, this is the function y. Maybe this is not the best way to do it, but y, if y is equal to 0, that means x must be 6, and this expression is going to be just 6. Okay, and something happens here. So fy has a local what? Well, if the first derivative is 0 and the second derivative is positive, then it has to have a local minimum. So graph will go like this. okay? And then it's going to go up this way. Because x and y both have to be positive, x has to be between 0 and 6, y also has to be between 0 and 6. If y is 6, that means x is equal to 0, and it'll be 0 plus 1/2, 6 squared. So this will be 18. Okay, but it doesn't really matter. The point is the minimum, local minimum has to occur here where y is equal to 1. And then x is equal to 5 because the sum has to be 1. And that's the answer. The two positive numbers, x and y, such that their sum is 6, and the expression x plus 1/2 y squared is minimum. That happens when y is 1 and x is 5. Let's go ahead and try to figure out what that is. X plus 1/2 y squared under these conditions is 5 plus 1/2 1 square, and that's going to be 5.5 or 11/2, and that will be the minimum. Okay, you notice here it starts at 6, which will be 12/2, goes down a little bit to 11/2, and then starts to go up again to 18. And so that would be the minimum value of that expression, x plus 1/2 y squared. All right, finally, number 11. It has 3 parts. Sketch the graph of the function satisfying the following. You probably do not like this kind of expression or question, but you may as well get used to it. These questions will really, really make you think and make you use your knowledge and the mastery of calculus concepts. F is defined on the closed interval 0 to 6, except at x is equal to 3, where you have a vertical asymptote. Okay, so what do we have? Let's draw a nice picture here. We don't know what this looks like, but we do know already that, let's use a different color for this. We do know that when x is equal to 3, you have vertical asymptote. Okay, so that's a nice way to draw a vertical asymptote. Let's go ahead and do that. Okay, and then it goes to 6. The graph function is defined between 0 and 6. F is negative wherever it's defined. That means anywhere between 0 and 6, except at 3 when the function is not defined, the function is negative. That means, look, that means the function, the graph is always going to be below the x-axis. This part is going to be excluded region. Graph will not go into the upper half of the plane, right? And then finally, it says f is increasing on 3, 6, and decreasing on 0 to 3. So what do we have? So increasing means just going up, okay? So we don't know what it looks like, but it's going to be something like this maybe. All right, so f is increasing, increasing on 3, 6 and decreasing. So it's going to be here. Let's get rid of that point or the curve or the point. How do I, oops. Okay, so I'm gonna undo this. Let's undo more. Yep, okay. So it's always going to be negative. So let's say you start here and it's gonna go down. And you have to have an asymptote. Asymptote means it has to keep going forever like this. And it has to increase from 3 to 6. So the graph has to go like that, and it stops right here. And it has to go down in both, from both directions, it has to go to negative infinity. It appears. The reason is I can't go this way because, well, between 0 and 3, the function has to be decreasing. So this is not possible, right? We don't know where it starts. It cannot start up here. It has to start below the x-axis, and it has to go down to negative infinity as x approaches 3. And then after 3, it has to be increasing. So the graph has to go like this. Again, never goes up above the x-axis. Okay, so that does the last question for you. If you have any questions, please contact me and try to figure out what you do not understand. All right. So I hope you feel ready for chapter 4 and your test on chapter 4.